Hello! So today we're going to change gears a little bit from the web server, and I'm going to start talking about cryptography. Now, before we get into this subject, I want to offer a disclaimer that this is a fairly complex subject, and I am in no way an expert on it. But I was also in no way an expert on web servers, so here we all are. What we're going to do today is begin with some of the fundamentals of cryptography, and really what we need to do is look into the data types available to us in C and discuss how they are actually insufficient for what we need to do. So let's begin with talking about numbers and precision. Oftentimes in cryptography, we are dealing with absurdly large numbers with hundreds of digits, and C cannot handle such numbers. I can demonstrate this here. So if I create an integer, and we'll just call it x, and I'm going to use hexadecimal numbers to display this. So I'll say 0x, and then f is the largest hexadecimal character we can use, and I can just keep typing some f's. And once I get to 16, I did not count there, but you can see that I am implicitly converting an integer to a long here. What this means is that once I hit 8 characters in that hexadecimal number, I need to change this to a long data type because an integer is not big enough to hold that. And then I can keep adding some f's, so let's add a few more. And once I hit 16, there it was, you'll see that this number is too large to be represented by any integer type. So there is no data type that I can store a number this big in C. So we need a different solution here. And to give you some perspective here, if I create another long y, this, I have it on my clipboard, is a hexadecimal number representing a typical hash from SHA-256. And as you can see, this number is substantially larger than the maximum number we can put into a typical C data type. So let's delete these until we can see what is acceptable. It's just 16, but I don't feel like counting that, so we're gonna do it one at a time. I'll just do it a few. So you can see that this number, even this, is way too big for a data type in C. So really what we need to do is create our own data type. But C does not allow you to create your own data types in the way that I would like. Ideally, we would be able to take some arbitrary number of bytes and just say all of those bytes are representing some number. But we can't do that. So we have to implement a roundabout way to do this. And there are some good ways to do it and some bad ways to do it. Both of them work, but they are good and bad for particular reasons. So for example, let's look at my hash one here from a SHA-256 algorithm. I could do this as a character array. So I could say character pointer y equals, well, let's just say character array y equals this as a string. And that is okay, but it doesn't, it gives us a way to store this symbol in memory, but those symbols do not reflect the actual values that they are actually storing. So the character f in hexadecimal is 15. But in ASCII or UTF-8, the encoding that my system is using, that number is like 64 or something like that. I know that a is, well, a lowercase a is 97. So those integral representations in the actual binary of my machine do not reflect what those values are in hexadecimal. So if I want to take this string and do some mathematical operation on it, then it won't work. Or at the very least, I'll need to use some very complex programs to say that F is going to be 15 and E is going to be 14. So we're going to take 14 here and then add it to something else later. And it just really is an unfortunate way to do things. So our other option is to use an array well, that was an array, but we're going to use an array that actually reflects the data type, and one where the internal hardware is synonymous with what is actually stored in the array. That'll make more sense when I show you. So instead of creating the number as a string, we're going to put it in an array. And what we can do is say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we can put a comma space, 0x to set another hexadecimal number. And we can repeat this process to keep each one within the bounds of what is acceptable in C. And we'll use a different data type. So we'll call it uint 64 underscore t. And that is an unsigned integer that is guaranteed to have 64 bits as its data type. And we'll need a library for that. There's the standard library, but that data type is basically the same as typing unsigned long. It's just kind of a shorthand. So we also want to be careful how we do this. So I started at this end and counted 16 after the x. And really what we want to do is start from the other end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that is where we're going to put our hexadecimal number. But there's still a problem with this, and we are going to need to think about this problem in the future. So again, if we want to do mathematical operations on these, we can do it one element at a time. But there is the possibility of an overflow. So what happens if this last element is 16Fs? That is the largest number you can store in a 16-digit hexadecimal in C. So if we want to add even 1 to this, we're going to get an overflow. And C isn't really going to tell us this is an overflow. We're just going to lose precision. So the output of that arithmetic is going to just be wrong. So we need to be careful how we detect an overflow. And there are 2 ways we can do this. One is to limit what the user can actually put in. So each element of this array can handle a 64-bit binary integer. But we could say instead that it handles a 32-bit binary integer. So this would be 8 digits instead of 16 digits. And then we could add anything we want to this, and we are guaranteed to still fall within the bounds of 1 element. So we won't lose any precision there. And that's a really easy thing to do. We can even allow the user to break that rule, and we'll just print an error message out to the screen when they do. But again, there's a problem here. So if we imagine they create this arbitrarily precise number, and then they add another arbitrarily precise number to it, then the result of that is no longer half of what could be stored in one of these elements. So we could end up with FF at the end of that. And now if we add something else to this, we are back in the same position of having to detect these overflows and losing precision through them. So if the user wants to do more manipulations on the result of a manipulation, we're going to run into problems. So what would be better is to implement a system that will detect these overflows and handle them in an intelligent way. So that's what we're going to do. But today we are just going to worry about creating our arbitrarily precise integer as a data type to use. So I'm going to create a new section of the library, and we'll call it Cryptography. And here we're going to create a new file. I'll probably end up putting this in a subdirectory, but you don't want to watch me make directories here, so let's just get on with things. And we will call this, what are we going to call this? A integer, and we'll call it unbounded int. Integer. I'll probably change that name in the future. So we're going to create a struct, and we need to be in the .h file, not the .c. And we'll call it unbounded integer. And here we are going to want the standard library. This is going to give us access to the uint64 data type. And we'll call this the integer. And this needs to be a pointer because we're going to do this as an array, and we want this array to be some size that we don't know at this point. So we are going to use a pointer and use malloc later to put our actual integer on the heap. So we have that. And one important thing to notice here is this u. So this is an unsigned integer. If we think of a binary representation of something, so 1, 2, 3, 4, 5, 6, 7, 8, so that is 1 byte. And all of our data types are based on bytes in C. Now, if this is a signed integer, this first byte is either going to be 1 or 0. And that is going to tell us whether this value is 1 or -1. So since there's a 0 here, this equates to 1. But if I put a 1 here, this equates to -1. So that is a signed integer. And we lose whatever that could be in binary as a size. So if we change this to an unsigned integer, this will now be, I think it is 157 off the top of my head. I'm not actually sure. It's 2 to the 8th power plus 1. That is going to be our result for this. So we have to decide whether we're going to use signed or unsigned integers here. And if we are using an array, and this array is going to store a number of sections of our large integer, our big number, then we want them all to be unsigned. And what we can do is create a short data type called sign, where the user can actually specify 0 or 1 there if it is a positive or negative number. And then we can just apply that one sign to the entire array. And that's an easier way to do it, and it also gives us much larger individual elements in the array. So then what we also want is an integer that is going to be the size. And this size is going to be the number of elements in our array. So how many individual 64-bit numbers are we going to need to represent this whole number? And then last, I'm going to create a character pointer, and I'm just going to call this hex. Again, I'm probably going to change these variable names later because I don't really like them off the top of my head. But this character pointer is going to be just a simple way for the user to view what this is actually storing. So this character pointer is going to take that entire array and basically condense it down into a string. So if we go back to our main function, what we'll end up with is a character pointer, we'll call it y for now, and it will end up printing that. That way the user can have an easy way to access just what the raw data looks like. And this is really just for aesthetic purposes. So if you want to see it, or if you want to print out what the hex digest of something is, that will be what this character pointer does. So let's go ahead and implement a constructor for this. So we will call this struct unbounded integer, and we'll call it unbounded integer constructor. And we are going to pass it first the sign, so short sign, and that'll either be 0 or 1. And then we're going to pass it the int size, that is the number of elements. And then we're going to use an ellipses to pass in a series of subsequent arguments. And we'll use those arguments to actually build the array of integer. And that's all we need here, but we will want a destructor as well. So we'll have void oops. And we'll pass this a pointer to a struct big num. I'm going to change that name later. Okay. Now, before we go any further, let me just point out why I know I'm going to need a destructor here. So you may have noticed if you've been following along with my other videos that I do not include destructors with every single class that I make. And the reason for that is I don't always need them. And the reason I need them in some circumstances is that I use malloc to allocate heap memory to some of the parameters in one of my structs. And if I use malloc, I need to be sure to use free. If you don't use free, then you are going to end up with what is called a memory leak. This is where you have allocated some space on the heap or somewhere in memory, and you lose access to it without actually clearing it. So that block of memory is forever taken up by whatever you've put in there, and you no longer have a way to access it. So it's wasteful, and it will make things run exponentially slower over time. So we need to make sure we free things anytime we allocate them. And since I know I'm going to be allocating space for this and this, I'm going to want to have a destructor. Okay, so let's move on to the implementation. So this one is going to be the constructor, and let's just copy these prototypes. All right, we'll start with the constructor. And what we're going to need is the standard arguments library. So we'll include standard arg.h. And here we are going to actually create an instance of our unbounded integer. So struct unbounded integer number, and at the end we are going to return number. So the first thing we want to do is create this va_arg data type. And this is going to allow us to access whatever the user has passed in to these ellipses. So the ellipses allow us to pass in an arbitrary number of arguments. We can pass in 1, we can pass in 5, we can pass in 0. We just need some way of specifying how many there are, and then we can access whatever the user passes in. So we are going to create a VA list, and we're going to call it blocks. And these are going to be the blocks that the user has specified. So if we take a really long number and cut it up into chunks, I'm calling those chunks blocks. We could call them chunks too, or sub numbers, whatever we want. I'm calling them blocks. And what do we need this to do? Nothing yet. We just wanted to say VA start, and its access point is going to be blocks. So that is the list that we are using. And the parameters are going to be size. So that is the number of items in the list. And then we can iterate over that list. But before we do, we want to set something up in this number variable. So number.integer, which is a pointer, equals malloc. And then we want to pass in its size. So our size is the number of bytes. And we want to multiply that by, well, instead of multiplying it by anything, we'll just use size of an array of uint64t with the number of elements of size. That will give us exactly the number of bytes we need. So we have this all set up. So integer is ready to accept some numbers as its individual elements. So we're going to create a for loop. So for int I equals 0, I is going to be less than size, and then I plus plus. And here we are going to say number.integer I equals, and then va_arg, access point is going to be blocks, and the type is going to be uint64t. This va_arg and va_list setup works kind of like a pointer. We essentially have a pointer called blocks to all of the subsequent parameters in those ellipses. And we know how big it is total, and we know where it starts. So here in va_arg, what we are doing is saying take whatever is currently being pointed at, and then move that pointer this size number of bytes in the desired direction, whether it's left, right, up, or down, however you want to conceptualize it. It will move it in that direction. So essentially it will point this to the next item in the list. Timer, excuse me, very professional. Anyway, We have set the element in position I to that number, and here is where we could do a test. So if I wanted to force the user to always make them half the size of what is possible, what I could do is say if number.integer I is greater than the hexadecimal representation of the max 8 character thing I can put in there. If it's greater than that, I can use p error, which is not included because I don't have standard input output, or I could just print f a warning message, whatever I want. But I know that I am going to actually implement an overflow feature, and so I don't really need to worry about that. So we have initialized the elements of integer. Now let's say number.sign equals sign, number.size equals size. And last, we want to set up the character array. So we are going to say number.hex equals malloc again. And here we need the size. So we can think of each individual character of these being a single byte. So we need the number of bytes total. So if we take the total size, so the number of individual arguments that are being passed in these ellipses, and multiply it by 64, I think will be correct. Is that right? Or 8? So we need the number of bytes, and a uint64 is 64 bits, which is 8 bytes. So we'll multiply this size by 8, and that'll give us the number of bytes we need to represent every single character. And then we can go through and actually initialize all those. So again, well, we could save some time here, could we? For the sake of clarity, I'm not going to. I'm going to do this individually first, and then I'll show you how we could save some time in this process. So we're going to again say int I equals 0, I is less than size, and then I plus plus. So now we're going to iterate over each item in number.integer. And what we can do, we'll need a few includes, so include string.h. And what we're going to do is basically take those numbers, put them into a character array using the sprintf function, and that is going to allow us to parameterize a string with an incoming hexadecimal, and then we're going to concatenate that string with what is saved here in number.hex. So you'll see, it's not as bad as it sounds. So we're going to define a character pointer inside the loop. That way we get a new one each time. So this is going to be character pointer x. Well, actually, we can just say character x. And we know this is going to be a size of 16. And we know that it's a size of 16 because each number is at most 64 bits. And the character that we are wanting is going to be, it's in bytes. So if each one of these arguments is 8 bytes. Am I thinking of this correctly? I'm sorry, not 16, but 8. So we can define a character array that has 8 characters. Each character is 1 byte, so we know that this character array has 8 bytes. And we know that each of these elements is a uint64, so 64 bits. That again is 8 bytes. And so we know that this will be sufficient to handle whatever we need. And let's give it a better name. I'll worry about the names later. So what we are going to want to do first is sprintf. And where is that defined? Is that in... I think it's standard IO. There it is. Okay, so the restrict is where this is going, and we're going to put it in X. And then what we want to pass in, you can see that there are those ellipses here again, so we get to see someone else use that. We're going to pass in a string literal. So what this is going to do is take a code, and this code is going to be %LL_X. And that is going to represent a hexadecimal number of long, well, long. So basically this. It's going to use a hexadecimal representation of whatever this number is. So it's a bit strange to kind of work out, but it's kind of a regular expression if you've ever worked with those. If you are working with cryptography, I hope you at least know the idea of a regular expression. So anyway, this is going to use a regular expression, so the argument we want to pass in is going to be number.integer I. That'll give us the particular one we are looking at. And then what we're going to do is call string cat. The source, or the one we want to concatenate to, is going to be number.hex, and we want to give it x. So that is just going to pile all of them on top of each other till we get a long list of them. And then for our destructor, all I need to do is say, give it a little space. So we're going to free big num arrow, since it's a pointer, hex, and free big num integer. And that's it. That's all we need there. Those are the only things that are allocated, and this is not calling any other of my data types, which makes it pretty easy. So that is our destructor. So let's test this out just to demonstrate that it actually works. So how are we going to use this? So first we're going to include /cryptography. I don't know if I've made this clear, but when you're actually using the library outside of the library, you don't need to use the paths like this. The actual include statements are a bit different outside of the library. I'm not going to go over how you do that right now, but just be aware that it is different. Anyway, we're going to include unbounded integer.h. Definitely changing that name. It's a terrible name. And, well, maybe it's not. I also kind of like arbitrarily precise integer. That's kind of funny. I might do that. Anyway, we're getting not sidetracked here. So we're going to define a struct unbounded integer. We'll just call it x. And we're going to set it equal to the constructor. Its sign is going to be 0, since it is going to be a positive number. The size we are going to want, well, I don't know the size yet. What we're going to do is copy this, and we're going to paste it into these ellipses. And what we can do is say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 0x. And then again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 0x. So we're breaking this up into those blocks, and then this, 14. So that is our last one. This is a total of 1, 2, 3, 4 blocks. So we can pass in 4. And then what I want to do is include the standard input output. And we'll say printf. And I want to print x.hex. So let's run this and see if it works. It's fine, I don't mind. Takes a second when you run it the first time. Uh-oh. What went wrong here? Well, we can see that the block is correct, at least. 446F, 6E2, 446X, 44F6, 446F6, E2. It's missing some components. Oh, okay. When I defined this, first of all, when I defined this, I was correct the first time. It is 16, because since I'm dealing with hexadecimals here, there are 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 in the other ones. 16 is the max, so I want 16 characters, and it doesn't have anything to do with bytes. So my mistake there. I apologize for confusing everybody, but let's continue on. Now, is that also going to be... Yeah, so I think that was the issue, is that this was too large to fit in a character array of size 16. So let's try this again. Nope, still doesn't like it. And this time it didn't work on the second one. That one has 15 characters. Why did it not like that? It's just saying it's a bad instruction. Let's give it a little more space here and see what happens. That seems unnecessary to me, but maybe I just put a comma in the wrong spot. Well, there we go. Did I put a comma in the wrong spot? I'm going to count these. I'll probably cut this out of the actual video, but... So those are all the correct size. Those are all 16 hexadecimal characters. We are not counting that 0x. That just tells the system that I'm using hexadecimal. So what is the problem here? 16 should be sufficient. Why wasn't it, though? So looking at this, well, I can't much see what's in there. It seems that when I set this to 17, it works, but when I set it to 16, it doesn't. That is a bit strange, but it works, so that's okay. So let's actually copy this, and let's put them side by side. Well, before I copy that, let me just put it down here. That's the original. And this, oh, give me the E. It didn't give me the E. I'll type it. And at first glance, that appears to be correct. So we have a way of storing these numbers now. And the next step is going to be to start performing operations on them. So how do we add two of them together? How do we multiply two of them together? And there are some fancy ways of doing that that'll make this a lot easier, but we also need to make sure that we handle any overflows. So we'll have to do some testing to see if there will be an overflow, and if there will be, we need to proceed with caution. So we will deal with that next time. I hope this was a good introduction to the sorts of problems we're going to be facing as we talk about cryptography. And this will be sort of the basis for more interesting things that we do in the future. So I hope you will stay tuned for that. I hope you enjoyed this video. Feel free to leave a like if you did and subscribe to the channel. I will see you next time. Toodaloo.